Next, let's look at a few modifications to our simple Rankine cycle. So what happens if you lower the pressure? Okay, what's going to happen is it's going to increase the work out of the turbine, but it will also require more work at the pump. The net effect is an increase in net work. It doesn't change the heat transfer at the boiler. It does change the heat transfer at the condenser, and so the thermal efficiency should increase. But there is, of course, a practical limit. Unfortunately, you can't lower the pressure exiting the boiler or the turbine too much because this will form extra liquid. The turbine requires a gas because liquid is going to pit the blades of the turbine. Okay? So generally we use a rule that says that I want to make sure that the pressure in the turbine is always high enough so that I have a quality greater than 90% at all points in the turbine. So here's another variation on this. I've changed the condenser operating temperature, which is equivalent to lowering the pressure. And if I do that, before I had an efficiency of 10%, now I have an efficiency of 12%. And again, pause this, go through the calculations, make sure that you agree with them. So I improved this, but if I look, the quality has dropped, so now the it's coming out is only a 93%. It's still safe, it's above 90%, but it is lower. I also could superheat the steam in the boiler. Then it will have more energy at that high spot, which can mean it produces more work. Okay, but I'm going to require more heat transfer at the boiler. So it's going to require more heat input to get more work. This actually can end up lowering the thermal efficiency, but sometimes we do it anyway, not for the sake of the efficiency, but to protect the turbine blades. So in this example, we raise the temperature to 95 degrees C. So we're superheating the vapor instead of just heating it to saturation at 85 degrees C. We're going back to the original 40 degrees C problem, but now we're going to superheat the material exiting the boiler. If I do that, I go from a thermal efficiency of 10.2 to a thermal efficiency of 10.5. So I actually did improve the efficiency a little bit. And if I look at what's exiting the turbine, it's still superheated. So there's no liquid at all forming in the turbine. So what if I increase the pressure at the boiler? Well, again, it can increase the efficiency, but you're going to require more work at the pump to get it to that higher pressure, but you'll get more work out of the turbine. Do it, but again, keep that eye on the quality to make sure that you do this. This is one of those modifications that you need to try it, see what happens. So in this particular case, the modification is that it's going to leave at a higher pressure and the temperature of the condenser is still 40 degrees. And in this particular case, we went from a 10.2 to an 11.3% efficiency. So it's saturated at a higher pressure. I was able to get more work out, and it compensated for the extra work of the pump. So this was a more efficient cycle. But other variations we can do are more complex. So sometimes I realize that it's starting to reach that critically low quality steam in the turbine. And so what I want to do is perhaps help the thermal efficiency, but more than anything, I want to protect that very expensive piece of equipment, the turbine. So I can pull the material out of the turbine early and reheat it and send it back into the turbine to finish the job. Okay? Now that will probably lower the thermal efficiency, but it will protect the equipment for minimal additional cost. So this is sort of what that device looks like. The turbine is probably technically one piece with kind of a dividing wall, let's call it. And here I'm going to take the material out, send it back into the boiler, a different section of the boiler, different piping, but the same piece of equipment, and then send it on through the rest of the turbine. Otherwise, the cycle stays the same. It's just that I'm removing some material early, reheating it, sending it back in to finish the job. So we're going to still assume that the heat transfer devices are going to be constant pressure. Boiler and heater are going to stay at a quality of 1. The condenser is going to cool to a quality of 0, so it'll be saturated liquid. I'm going to assume that my ideal pump and turbine are reversible and adiabatic, which means isentropic. And the net work is going to be the work from all of the turbines and all of the pumps, however many I need. And the heat for the boiler is going to be the heat for all portions of the boiler. So in this case, I'm going to take the material out of the turbine when it reaches a pressure of 1.5 megapascals. I'm going to reheat it to saturated vapor and then let it expand the rest of the way down to that pressure of 1.0164, which is where the condenser can operate at 40 degrees C. So I'm going to have a pump, but I'm going to have 2 stages of the turbine and a boiler and a reheater plus the condenser. Again, pause the video to really look at this example in detail, but what you'll see is that the thermal efficiency has dropped from 10.2 to 9.9%. However, I now have a higher quality coming out of the steam, out of the turbine. So at all points, the quality of the steam is higher now. So we're going to pause again here. We're going to come back. We'll talk about a final major modification to the Rankine cycle. And then we will also talk about reality when I have process efficiencies that I have to figure in there.